Hello everyone. In this video, we will give a brief introduction to numerical integration. Alright, so what is numerical integration? So something that's pretty simple to do here is this integral, right? So you would get sine of x from 0 to pi over 2. You'd use your fundamental theorem there, right? And then we'd see that we get sine of pi over 2 minus sine of 0, which is going to be 1. And we get an exact answer, and we're happy, maybe. And so what's an issue is that what if we had had cosine of x squared here instead of x? Now this seems like it shouldn't make a big difference, but it turns out that it really does. So cosine of x squared does not have an antiderivative that we can write in terms of these elementary functions that we know how to deal with. And so this is an example. Another one would be e to the minus x squared. These guys don't have an exact answer. And so when we don't have an exact answer for our integral, then the best that we can do is to approximate it. And so what we're going to talk about in this video are some ways to approximate this, which we're going to kind of go back to Riemann sums a little bit and talk about using areas of rectangles and trapezoids to approximate these answers. And then we'll talk about their error bounds because, of course, if we're approximating, we would like to know how accurate we are being in our approximations. And so this is the idea behind numerical integration. Okay, so since, cosine of x squared, e to the minus x squared don't really have numbers that are nice to just kind of quickly plug in and stuff like that, we're just going to talk about 1 over x here for our examples because it's just going to be a little bit easier for the numbers. But of course, I am aware of the fact that yes, you can just get the natural log of 3 from this because we know the antiderivative of 1 over x. So let's go ahead and look at the different sums that we're going to talk about for approximation. So we'll talk about 3 of them here and then a different one soon. So first, our left sum, which we'll denote by Ln. So for all of these, we're going to, at least for this one, have n equals to 4, which is the number of rectangles. And that our width delta x is going to be b minus a over n in general. So here that's 3 minus 1 over 4, or 1/2. So that's just our width, right? So we're going to go to 1.5 and 2.5 here as our other points. So we want 4 rectangles. And so our left sum is determined by the left endpoint of each of these intervals, right? So I'm plugging in 1 to get my height here, plugging in 1.5 here, I'm plugging in 2, and then I'm plugging in 2.5. Right, and so you can see that this is an overestimate. For your right sum, well, you use the right endpoints, right? So we're using 1.5, we're using 2, we're using 2.5, and then we're using 3, right? And so you can see that they share the 2 middle ones, but then the one on the left and right are different. So that would be Rn for your right sum. And then lastly, in green here, we'll talk about the midpoint sum, which we'll denote by Mn. And of course, there you're just plugging in the midpoint of each interval. So you'd be plugging in 1.25, you'd be plugging in 1.75, 2.25, and then 2.75. And you can see that the left and right are not quite as good of an approximation as the midpoint one, which kind of splits the difference and is clearly doing a little bit better in terms of accuracy. All right, so now let's look at sigma notation, which is going to give us a more compact way to write these sums that give us these approximations for area. So we'll focus here on Ln. So again, I'm using my left endpoints here to determine the heights of my rectangles. And so this is overall just a sum of areas of rectangles, right? And so then the question is, how am I getting this? Well, it's always the width delta x. So that I can just pull out. All of them are the same width, in this case 0.5, times the sum of the heights. And how am I getting my heights? Well, I'm plugging in endpoints to my actual function. And so if I say that f of x is 1 over x here, then in this case, specifically for L4, I would get delta x times f of 1, right, plus f of 1.5, plus f of 2, plus f of 2.5. And then if you actually do this out, this is 0.5 times 1 plus 2/3 plus 1/2 plus 2/5. And you can get an approximate answer of 1.283. Okay, and so now the natural log of 3 itself is about 1.099, and so we can see this is an overestimate, as our picture suggests, and that it's not super accurate, given that, you know, being off by about 0.2 when you're only a little over 1 is quite a bit of error. So then what is the general form in sigma notation? So again, you can pull out the delta x, just kind of to start, and then it's really just what is the sum of the heights. So we're starting at A to plug in, right? That's our leftmost endpoint. So here my 1 is my A. And then how do I find my next thing that I'm plugging in? Well, I'm just going over by the width every time, right? In this case, I go over 0.5 each time to find my next endpoint. And so I'm adding I times delta x, where I goes from 0, because the first point you just want A itself, to n minus 1, not all the way to n, because we stop here at, you know, in this case 2.5, 1 width away from the far right endpoint B. Okay, so this is the general form. All right, so to talk about sigma notation for the other two, well, first of all, Rn is very, very similar to Ln. So again, you can pull out the width of all of these things. And we're still plugging in endpoints in the same way. We're adding the width each time to find a new endpoint, right? Like, you know, we'd still be adding 0.5 each time in the case that we were just looking at. But here, we don't start at A, we start at the right endpoint of that interval. So we actually start when I is 1, right? We start with not A, but A plus delta x here. That's our starting point for our right one. And then we go all the way to n plus delta x, which is going to be B. Okay? And then for our midpoint sum, it's a little bit more complicated. So again, we have the delta x, we have the sum, and in this case, so we start with A, but then we don't want to add just the width each time, right? We want to get to the middle of the interval and then add. And so the way to capture that is to do 2i minus 1 delta x over 2. And so basically, when I is 1, this becomes 1/2 delta x. Then when I is 2, you get 3/2, 5/2, etc. And so you're always doing 1.5, you know, 2.5, 3.5 delta x. So you're always in the middle of one of those intervals. All right, so now let's look at the trapezoid sum. So in this case, how are we actually getting trapezoids here? Well, we're actually going to be kind of doing a straight line from the left to the right endpoint of each subinterval, and then coming down. So it looks something like this. Right, so all of our trapezoids individually here look something like this shape. And so if you remember the area of a trapezoid here, this is going to be base 1 plus base 2, but 1/2 of that times the height. And so our height here, since obviously this is kind of flipped on its side, is equal to our delta x as usual. And then how are we actually getting the rest of it? So again, you can like pull out the delta x, and then, well, we're basically taking the left endpoint and the right endpoint of each of these, right? So it's basically like combining the two pieces from the left and right sums simultaneously. So you actually want to do f of a plus I delta x. This is basically giving you your left. Plus, well, you want to go one width further, so I plus 1 delta x instead of I delta x to get your right endpoint of each. And then obviously you want to divide by 2 throughout the whole thing, and so you could just do the 1/2 on the outside. And if you were noticing there, again, you're just taking the average of the left and right here for each endpoint. So it turns out it really is that simple, that if you've already calculated your left and right sums, then it's just 1/2 the sum of those, or the average of your left and right sums. So for your first exercise, I just want you to compute the trapezoid rule, or the trapezoid sum for 4 trapezoids for the integral from 1 to 3 of 1 over x dx. So now let's talk about error analysis. So earlier we saw, right, that the integral from 1 to 3 of 1 over x dx is the natural log of 3, which is roughly 1.099. And we saw that our L4 was approximately 1.283. right? So it's off by, just under 0.2 there. So in general, right, this seems easy. You just kind of say, hey, this is the right answer. And you just compare your approximation to the right answer and see how far you are off. But again, if you have something like e to the negative x squared or 0 to pi over 2 of the cosine of x squared, there is no right answer here to compare to, right? And so if you don't know what you're comparing to, how do you know how far off you are, right? How do you know how accurate you are? So our next goal is to talk about how we can bound the error on our left sums, right sums, trapezoid sums, etc., and figure out how close these are without actually knowing a right answer to begin with. So we're not going to talk about all of these, but I'm going to focus mostly on the left and the trapezoid because the left and right are very similar, and the midpoint is pretty close to the trapezoid, but not quite as accurate. So if we let I be our actual value of the integral, then it turns out the error, which is the absolute value of the difference, right? Because this basically just says how far am I off, but doesn't take into account whether it's an underestimate or overestimate. That's what the absolute value is doing, is less than or equal to b minus a squared over 2n times this constant k1, which I'll get to in a second. And for the trapezoid rule, it's less than or equal to b minus a cubed over 12n squared times this constant k2. So obviously, as n increases, that's the main thing that matters because the rest of these are all constants. So you can see that the fact that we're dividing by n squared down here versus n up here, right? Dividing by a bigger thing means you're smaller. So there's going to be, in general, smaller error for the trapezoid rule than the left rule or right rule. So then the real question is, because you know what b and a are from what you're given, are what are these k1 and k2? So k1 is an upper bound on the absolute value of f prime of x on your interval. And k2, as you might suspect, is an upper bound on f double prime, or your second derivative, on this interval. So we'll maybe talk a little bit more later about why these actually come into play, but just, very quickly, at least for the k1, since the k2 is maybe a little bit harder to see, right? F prime is talking about slope, and so the steeper that your slope is, then if you have, fewer rectangles, the more error you're going to have, right? Like if I have very steep curve, and if I just go over a little bit, I can get a lot of error. Whereas if I have a very flat curve and I go over a little bit, I'm not getting nearly as much error there, right? And so this is why you should think that this derivative matters. And basically the second derivative matters for similar reasons. The concavity, the stronger this concavity you're seeing is going to determine how much error is happening. So as an example of this, let's look at our error for the one we've been working on, this 1 to 3 of 1 over x dx. So f of x is 1 over x here. And so f prime of x is going to be negative 1 over x squared, and f double prime of x is going to be 2 over x cubed, right? And so on the interval from 1 to 3, when is the absolute value of these biggest? Well, as the denominator increases, the absolute value is decreasing, right? And so basically, the max value that the absolute value of f prime can take on is 1. And for f double prime, since you have a 2 on top, this is going to be 2. And so your k1 here is 1, and your k2 here is 2. And so this is kind of a preview of how we'll be solving for these in general, although sometimes it just helps to do this graphically for nastier functions than this. So what do we know about our L4 then? So Ln in general is going to be off from this integral. So again, we'll call this I, just to not have to write it every time. Is going to be less than or equal to b minus a squared. So b minus a is 2 squared over 2n times our k1, which is 1. And that's just 4 over 2. And so this is equal to exactly 2 over n. And then our trapezoid is going to be less than or equal to, so b minus a cubed, so 2 cubed, over 12n squared times our k2, which is 2. And so you have 16 over 12, which is 4/3. And so we have 4 over 3n squared. So when n equals 4, what are we getting here? Well, this is off by at most 1/2. And this error is off by at most 1/12 because it's 4/48. So then some question you might have is like, okay, I want to maximize my error at this much, right? Like I want no more than 1/100th off. So how many trapezoids would you need, or what must your n be to have less than or equal to 0.01 error on Tn? So in that case, what would you do? Well, you know your error in general is 4 over 3n squared, and you want this error to be less than or equal to 0.01, or 1/100th. Well, so all you do there is just cross multiply, right? We can deal with these things. These are all positive here, and so you would just get 400 is less than or equal to 3n squared, and thus n squared is greater than or equal to 400/3. And this is where you can just pull out your handy dandy calculator. This guy is approximately 11.55, or sorry, when I take the square root. So n is greater than or equal to approximately 11.55. And so if you choose n to be at least 12, if you have 12 or more trapezoids, then you would have less than 0.01 error. So for your second exercise, I want you to find the n in a similar fashion so that the left sum has less error than 0.01. And then for your last exercise, I want you to find the upper bound on the fourth derivative's absolute value on this interval for 1 over x. This will be useful for talking about the error bound on what's called Simpson's rule, which we didn't introduce here, but we'll talk about more in class. All right, thank you for watching.